Greetings, Internet world. Brian here again, here with another episode regarding the rocket engineering. And today I want to talk a bit about what is known as specific impulse, or ISP, of a rocket engine. So without further ado, let's get started. In the previous video, I did not explain that force is just a change in momentum over time, but that was kind of obvious in the equations, I thought, but I thought I would just outright say it here. And so in its purest form, impulse is basically the integrated force on an object over a period of time, and that is going to create the impulse effect. So this effect can be brought into real world applications by thinking about what happens when a baseball player hits a baseball with a baseball bat. What he's doing is he's applying a force over, although it may be very short, a period of time, and that effect, which is a change in momentum of the baseball, is known as impulse. So here we have the impulse momentum theorem, and it just states that impulse is equal to the integrated force over a period of time, and as I just mentioned, force is equal to the change in momentum over time. Canceling these dt's out in the second integral listed here, you see that you're just left with the integral of dp. Solving for that integral, or integrating, is going to give you delta p. Now in the previous video I did an explanation on the classical physics representation of momentum, which is mass times velocity, and I mentioned that velocity of the exhaust gases was constant because the fuel and oxidizer chemical reaction gives a certain partial pressure that will give a constant velocity. So the only thing that's changing on the system in this regard is the mass, and therefore getting that in mind, we have the delta mass of the propellant times the exhaust velocity is going to give you the impulse. Solving for exhaust velocity, we get the impulse divided by the change in the mass of the propellant. Okay, so up until this point, I've been talking about exhaust velocity in the equations. In fact, we just solved for exhaust velocity as the impulse effect divided by the change in mass of the propellant. But really, what we're going to have to do is we're going to have to introduce a new parameter called c, which in human language is going to be the effective exhaust velocity, otherwise known as the equivalent velocity. This parameter c is going to actually be closer to the real velocity of these fluids as they fly out of the back of the rocket, because they take into account things like friction, changes in air pressure, and non-axial flow through the rocket, which is just what we have to account for in real life situations. Alright, so here is just written down what I just said. Sometimes it's easier to visualize. These explanations with English can become very verbose, so I find it helpful sometimes to be able to see what somebody's talking about rather than just hear them say it when regarding these types of technical things. And so as you can see, what we've been dealing with is this exhaust velocity here, VE. We're going to change that though. So the effective exhaust or equivalent velocity is going to be defined as c. And so if you recall this thrust equation that I introduced in the last episode, you know that the total thrust of the rocket is going to be much more than just m dot times exit velocity, and this second part here is going to be m times exit velocity dot. We're just going to simplify this greatly by introducing this c variable, and so you just get m dot c, and like I said, that's going to account for a lot of the real world parameters that you experience in real life when dealing with these types of things. And earlier, we just had exit velocity equals the impulse divided by the delta m propellant. We're just going to change that exit velocity to c because it's more specific that way. Okay, so up until this point, we've talked about the equation for c being the effective impulse divided by the change in mass propellant. That's pretty useful in explaining impulse, but we still haven't said anything about specific impulse. And so what we're going to do now is talk about specific impulse, which is it's an efficiency measure of rocket engines measured in seconds. And so let's do that now. So here I just rewrote the equation for C, and I also included the units so that you can see that C is a velocity. If you look at the unit cancellation, it just simply comes out to meters per second. We all know that's velocity. Now, ISP is going to be the new parameter that we're introducing right now. And as you can see, all we did was divided C by gravity. And so how that works out is it's basically going to be able to tell us the efficiency of a specific rocket under one standard Earth G, which we all know is 9.81 meters per second squared. It's an acceleration. And as you can see, the units right here, if you think about that, I kind of just did it in my head, but it comes out to be seconds. So feel free to write that out and check me on that. But this is the specific impulse of a rocket measured in seconds. It's important to keep in mind that this is an efficiency measure of a rocket engine. Okay, so what the ISP tells us is the total number of seconds that the rocket can apply thrust equal to the total mass propellant under one standard G, which is the Earth gravity unit, 9.81 meters per second squared. All right, to give some practical examples, a launch vehicle will have an ISP of around in the range of 200 to 500 seconds, where an ion thruster engine for deep space missions can have one up to somewhere around 3,000 seconds. But you might be wondering, why are they so different? So I think the whole idea it depends on what the mission is. I mean, launch vehicles are typically used to carry payloads to the International Space Station or to launch a vehicle into orbit. But if you're thinking about an ion thruster engine, I mean, that ISP is very high, but you don't typically see them launching ion thruster engines from a launch pad under the influence of Earth's gravity. You see those more used in things like the Voyager spacecraft. So vehicles with on missions that are going to be deployed for a very long time, they need to be very efficient in that regard. So again, the space launch vehicles have a much lower efficiency, but that's because their missions are different than, let's say, a deep space mission using an ion thruster. All right, everyone, so that concludes our episode on specific impulse of rocket engines. In the video, we talked about how specific impulses are different for different engines and the reasons why they are, and we mathematically broke down what ISP actually is. We talked about the effective impulse, and we talked about at the very beginning impulse momentum theorem. And so if you liked the video and enjoyed it, please subscribe and click the bell notification to be notified when I put more videos out there, and leave comments in the section below if you have any questions or you just want to tell me how it is and how you enjoyed it, maybe things I can add to it. So thank you all for tuning in, and I will see you next time.